Alright people, I hope we're doing well. On this one we're going to be changing the form, first with simplifying these expressions, or actually not really simplifying, just changing the form of them, and then doing so in the midst of verifying particular identities. I'm not going to be going slowly through these since, by now we should have a certain facility with the identities. If you want to challenge yourself to these problems, obviously there's a pause button, so I suggest you do that. Now it says write the expression as one involving only sine and cosine. Now in class we did one with sine of 2x plus cosine of 3x. Here it's been swapped. We also did one with sine of 4x, but here it's been changed into cosine of 4x. So if you've watched the video or if you attended online class today, you should sort of have an idea of how to do this. Now, we know the double angle identity, and this one is a triple angle. It's 3 theta. But we also know the sum and difference, and we can take sine of 3 theta and represent it as sine of theta plus 2 theta and use the sum formula. At which point we get sine theta cosine 2 theta plus sine 2 theta cosine theta plus cosine of 2 theta. Now, I mean, if you want to pull this over here and group them together, that's fine. It doesn't really matter. You're going to get a sort of a weird sort of half-factored expression at the end, but if you want to do it, that's fine. That way you really only have to deal with cosine 2 theta once, which is kind of nice, rather than dealing with it twice. You simply have to ask yourself which cosine of 2 theta you want to deal with. Well, this one is 1 plus sine theta, so if you want to, let's just go ahead and do it with the sine version. So I have 1 plus sine theta, and this becomes 1 minus 2 sine squared theta. This sine 2 theta becomes 2 sine theta cosine theta, and that of course is multiplied by the cosine theta, which just comes along for the ride. And you know what? I mean, you can multiply it all out. You can keep it all separate. I really don't care at this point. And the reason that I don't care is because it's not specified. It's not specified what you're going to be doing with this in future steps for this particular problem. So it actually is not clear how you should leave it. And you could multiply this out and then make this 2 sine theta cosine squared theta, and that's good enough. Whatever. I really don't see any benefit in going any farther than that. Like I've said before, simplification becomes kind of less important in calculus. It's not really a matter of simplifying. It's a matter of changing whatever you have into a form that is either usable, whereas the original was not usable, or more usable, easier to deal with. And sometimes that's by simplifying, but sometimes that's by unsimplifying, or turning it into factored form rather than polynomial form or something like that. So basically, we need to have facility with all of the variety of ways to change the form of something, and we simply need to be able to do whatever it is we need to do with it to get it into the form that we know we need it to be in for future steps in a larger problem. Enough on that. All right, cosine of 4 theta, like we said in class with the sine of 4 theta, this can either be conceived of as 2 theta plus 2 theta, but that's going to give you the same thing as if I reconceive of it as cosine of 2 theta, right? Because cosine of 4 theta, despite the fact that it's a 4, is still a double angle. It doubles 2 theta, just like cosine of 6 theta would double 3 theta, right? And so this one is correct, but let's go ahead and focus on this one. And so basically what happens is we get cosine squared 2 theta minus sine squared 2 theta. But that's probably not the best one to work with, because now I have to transform both of those, right? So again, I've gotten myself into a form that's probably not as easy to work with. Instead of this, let's actually jump to the 2 cosine squared 2 theta minus 1, and therefore I only have one of those double angles. And really, you got to remember that that square is basically means that, right? And so what we want to do is we want to use the cosine 2 theta, and you can, let's just do the cosine one again. So I have 2 cosine theta, or 2 cosine squared theta minus 1 squared minus 1. Now, that's not fun, but it's doable, right? And so we can do, 2 times 4 cosine squared theta minus 4 or that's supposed to be to the 4th, squared theta plus 1 minus 1. And then we can multiply it all out and get 8 cosine to the 4th theta minus 8 cosine squared theta plus 2 minus 1, or plus 1. And, you could have gone, in this one right here, this one could have alternatively, become 1 minus 2 sine squared theta squared minus 1. And at which point, you would have gotten an ultimate result in terms of sine. And of course, you could have broken it out and made it 2 cosine squared theta minus sine squared theta squared minus 1, and you could have worked it out like that and gotten it in terms of both sine and cosine. It doesn't really matter. What matters is the fact that you have a strategy of bringing it from 4 theta to 2 theta, simplify out, and then bringing it from 2 theta down to just theta, okay, and getting rid of all of those. All right, let's move on to some verification problems. I think those will be a little bit more fun since we actually have a specific target that we're aiming at and not just sort of nebulously changing the form. Now in this one, and like I said before, if you want to pause it to work on it yourself, that'd be great. Now notice that this has cosine squared over here. Well, I know that tangent squared has cosine squared as a denominator, and I know that that numerator can be sort of turned from one term into 2 terms, right? And in doing so, that will actually allow me to separate fractions and reduce. The question is, what form of cosine 2 theta? Well, if I change cosine 2 theta into cosine squared minus sine squared, then I'm only one step away, because when I separate the fractions, and I'll go ahead and show that step, I'm going to get 1 minus tangent squared x. Okay, and that winds up being fairly simple. Okay, now if you mess up and you do, 1 minus 2 sine squared theta or 2 cosine squared theta minus 1, you're not at a loss. I mean, you use the Pythagoreans to basically derive that second and third version of the cosine double angle identity, and you can use Pythagoreans to undo it and get yourself back to something that looks like this, so that you can then separate the fractions. You just have to be careful when you look at that denominator. You can also turn that into 1 minus sine squared. By the way, don't, okay? Because if you do, you no longer have a monomial denominator. Now remember, it's not a matter of whether you can do something. You can do an infinite number of things to either one of those sides, the left side or the right side. It's not a matter of what I can do. It's a matter of whether I should do. And should I take that cosine squared and expand it into 1 minus sine squared? Absolutely not. Alrighty. Let's go ahead and take a look at this one. we notice that the left-hand side has our double angle. Let's go ahead and work on that side. And I know that cotangent doesn't have a 2x. Now I could, there are a couple ways that I can do this. I can turn this into 2 over tangent of 2x. Now if I do that, I'm going to, wind up with 2 tangent x over 1 minus tangent squared of x. And then when I flip it over, I'm going to get 1 minus tangent squared of x all over tangent. And then, because the 2's cancel out, right? And then I can separate the fractions, and I'm going to wind up getting cotangent x minus tangent x. I can also, if I don't see that, I can just as legitimately turn this into that. Now, if I do that, and I wind up with 2, my cosine 2x can become cosine squared x minus sine squared x all over 2 sine x cosine x. The 2's will cancel, and then, despite the fact that there's 2 factors, that is still a monomial denominator. I can pull that apart into cosine, let me put a little dividing line right here, cosine squared over sine x cosine x minus sine squared over sine x cosine x. Okay, one of those cancels with the cosine in the denominator, one of those cancels with the sine in the denominator, and I get cotangent x minus tangent x. And both of those, of course, would be completely legitimate ways to do the left-hand side. Now, I wouldn't recommend doing the right-hand side, and I've already done this 2 ways, so I'm going to go ahead. But if you want to go ahead and test it out and see how more basically what you would need to do, let's go ahead and do it. Let me go ahead and get another piece of paper out. And this is merely for the sake of illustrating why one side is oftentimes done in lieu of the other. Now, let's go ahead, and we have 2 cotangent of 2x is equal to cotangent x minus tangent x. Now, what can you do with the right-hand side? Well, the only thing you really can do is, turn it into its implied fractions, and then the only thing you really can do at that point is maybe turn it into by means of common denominator, that. But then you actually have to see, the whole, well, if I put a 2 here, then I have to multiply by 2 out here. And only then can you turn the numerator into cosine 2x and the denominator into sine 2x and put the 2 out in front, which then becomes 2 cotangent 2x. Now, if that makes sense to you, then by all means do problems like this in that manner, okay? I see that as a little bit harder to see. You're kind of meandering unless you see this and automatically can see 2 steps ahead in your head. Then you're probably better off working this left side one of these 2 ways. All right. Let's go ahead and take a look at this one. Cosine of 2x is equal to cosecant x minus 2 and over cosecant x. Now, you're thinking to yourself, cosine of 2x doesn't have anything to do with cosecant, at least not on the face of it, but it does have something to do with its reciprocal, sine squared, okay? And you're like, that is a little bit interesting. Why don't we go ahead and see what happens if we multiply both sides by sine squared? If we multiply both sides by sine squared, we're going to get 1 minus 2 sine squared over 1. And of course, that is cosine of 2x. So that was basically, 2 steps, or, more like 1, but whatever. So basically what happens there is you have to see the cosecant, and because here's the thing, the strange thing here is the 2. The 2 is the biggest clue, which tells us that it might be the 1 minus 2 sine squared x. And the thing is that if you see that 2 and you're like, oh, only if that 2 was right next to a sine squared x, that ought to remind you that if I multiply the numerator by sine squared, I also have to do the denominator, and that will make the denominator absolutely evaporate. Okay? Now, this one down here, actually, I can actually see you doing it either way. Because the left-hand side, the factorization should be really easy to see. Okay? And so let's go ahead and take a look at the left-hand side. I know that if I factor out a sine x cosine x, which of course would be, the GCF, I get that. Okay, well, this right here is a recognizable double angle identity. This right here is not until you provide the 2. Can you do that? Sure you can, if you also then multiply by 1/2. And what we get at that point is this becomes, of course, this is sine of 2x, and this is cosine of 2x, and I probably should have done that little notation in red, but whatever. And I get 1/2 sine of 2x cosine of 2x. Now, that might be a little more difficult to see, but remember that when we did the sine of 4 theta, this right here was part of the next step, okay? And we've already seen the fact that providing a 2 has given us 1/2. If we provide another 2, we're going to have to provide another 1/2, and that's going to give me my 1/4. So if I have this, let's push this 1/2 out here, and I have sine of 2x and cosine of 2x. In order for that to be the double angle identity for sine of 4x, I need a 2 and another 1/2. At which point I now have, here's my 1/4, okay, and this right here is double angle for sine of 4x. And so it was just sort of 2 layers, okay, and cha-ching. All right, let's go ahead and take a look at this one. Like I said, I'm going to kind of continue mowing through these just to make sure that we don't... just to make sure that there's time enough to get through all of these in a reasonable amount of time, so that the video isn't forever long. And like I said before, you can always pause it. Alrighty, let's go ahead and take a look. Okay, it says prove or verify. Now prove that that is secant x. Okay, well let's go ahead and take a look at it. I know that if I go ahead and expand those numerators, because I have no reason to believe that it would be anything else, I get 2 sine x cosine x over sine x. But I also remember that cosine of 2x becomes a binomial, and I can actually put those independently. I can put those independently over the denominator. The question is, which of the cosine 2x identities? Well, it doesn't really matter, because some of these things will sort of cancel out, and you'll wind up being able to change the form again. But I know that if I want a 1 over cosine, I'm probably going to use one of the identities that actually involves either the 1 minus 2 sine squared x or the 2 cosine squared x minus 1. And I'm going to go ahead and do the 2 cosine squared x minus 1. But the hard part about this is I need to put brackets here. Because if if this turns into two terms by means of identity, this negative needs to be distributed across it, largely because that numerator and that denominator are implied parentheses. And so I have 2 cosine squared x over cosine x minus 1 over cosine x. Well, that's going to be really convenient because that cancels out with that. This cancels out with one of those. And when I distribute the negative, I'm going to get 2 cosine of x minus 2 cosine of x plus secant of x. Those cancel out, and I'm just left with secant x is equal to secant x. Alrighty. Now, this next one I'm pretty sure is a typo, okay, because 2 tangent x over 1 plus tangent squared is not a legitimate one. But let's go ahead and test it to see, right? And here's the way I'm going to do it. 1 plus tangent squared is actually, because here's the thing. Actually, it's not a typo, because here's the thing. When I have, gosh, that sort of head faked me for a second there. Tangent of 2x is equal to 2 tangent x over 1 minus tangent squared. What they're asking you to do is see whether changing that will ultimately completely change the identity. And in fact, it actually will, because 1 plus tangent squared is actually secant squared. And that means, okay, because if you're dividing by secant squared, you're dividing by a quotient. If you're dividing by a fraction, right? And so if you're dividing by a fraction, I'm going to go ahead and take the numerator and basically put the tangent as its implied fraction. And then I'm going to multiply by the reciprocal of the denominator. This cosine cancels with that cosine, and I'm just left with 2 sine x cosine x, and that is sine of 2x. And that, of course, is exactly what I was aiming for. And it looked a little bit hinky at the beginning, but it wound up being just fine. These are the verification problems for double angle identities. There are obviously, tons and tons of more examples, and we'll go over some of them tomorrow. But I think this is a good representative sampling that allows us the opportunity to continue to play with identities, and to certainly play with these new ones, these double angle identities, in order to familiarize ourselves with them so that we can then, when called upon, use them strategically when we get to calculus. Okay, that is the end of video 2. I will go ahead and do the equations in video 3. If you have any questions, as always, please do shoot me an email or a message on Teams. Bye.